So thanks, Philemon and Thibaut, for organizing this series of talks. And so as advertised, today I want to talk to you about lion hunting, which is a subject I find quite interesting because quite a few people know about it and actually connects a lot of areas of mathematics. Maybe a bit of a warning. It's going to be kind of a light talk. We're not going to go deep into very abstract mathematics straight away. I thought, since it's only maybe a second ZUCMAP this term, we can start slowly. So today's talk is going to be in three parts mainly. First of all, I want to introduce to you what lion hunting is. And then there's going to be a second part, which is going to be mainly pointed topology, or like an introduction to it, because these are things we're going to need in the third part, which is going to be like one of the versions of lion hunting that I want to introduce to you. So maybe first of all, what's lion hunting? I'll write some things down, it's not too important. So it's actually something that arose from like crazy fun part of mathematicians, I don't know. It was initiated by a mathematician called Ralph Boas Jr. So he was a fellow of the American Mathematical Society in like the 40s, 30s, 40s. And he wrote first a paper, and then there's even books now, I think, under the pseudo H. Petach, some like joke papers, let's say, that initiated the lion hunting. So what's lion hunting? How can we hunt a lion in mathematics? So we need to formalize this. And how we do this is that we say we have a lion, and we have the Sahara, which in our context is going to be kind of like a bounded space. And we have infinite time. Yeah, that's not very realistic, I know, but well, that's how we do it. And then we have one axiom that is there is a lion in the Sahara. Okay, so that's how you do it. And then the challenge was kind of like using mathematical tools. How can we capture the lion? And so let me introduce like a couple things that have been done so far. It's going to be maybe a bit more advanced because it's like the edge of the research. But I'll just give maybe a sketch to give you kind of a brief idea of what you can do. So let me present three methods of hunting the lion that have been done so far. The first method is the Peano method. And so what Peano has done is he has shown that if you have a plane, you can construct a curve that fills every point of the plane. So you make such a curve through the Sahara that goes through every point. And then we also know that we can go through such a curve in as short as we want. So what we do is we take a spare, and we go along this line through the whole Sahara, faster than the time that the lion needs to kind of move its own length. Then we're sure that we caught the lion. It didn't get the chance to move before we got it. So that's the first one. The second one, that's my favorite because it's also a bit topological. And I like topology, as you'll notice, is the topological method. So that's, again, weird words, but basically what you say is that for topologists, the lion is like a torus, because like, yeah, there's the mouth and the butt. And what you do is you transport the lion into 4 space. And then in 4 space, what you know is that any knot can be undone or done. So what you do is then you knot the lion in 4 space, and then you bring it back into the Sahara, and then it's gonna be knotted. So you can maybe do a knot like this. Then, well, it can't do anything, and you just pick it up. Why you can unknot knots in 4 dimension? Maybe intuition. If you have, if you do 1 dimension lower, because like 4 dimensions is hard to picture. If you have the plane and then kind of you imagine a line that would be like kind of your separation in the plane, and you have a point on one side. You can't move that point to the other side of the line without crossing the line. But if you add a third dimension, then you can kind of just take it and put it on top. And in 3D, it's the same. If you add one dimension, you can kind of take the strings and just put them on the other side without intersecting. So that's why we can knot the line. All right, and then the last method is the Schrödinger method. That's for physicists about in the crowd. Is quantum physics. You just put a cage in the desert, and you know that at any time there's a non-zero probability for the line to be in the cage. So you just wait, and eventually it's going to be in the cage. All right. So that was it for the fun introduction. Now we'll need to get some weapons ourselves to be able, at the end of this talk, go hunt the lion ourselves. The method I'm going to introduce is, so it's going to use topology, and I think it's maybe a bit more useful than the funny things I just presented to you, in the sense that it's kind of a method of proof, which I find very nice and I think can be useful in general. So here we go. Let's do a quick introduction to, or quick, I don't know if it's going to be quick, to topology. By the way, if you have any questions, feel free to just interrupt me, or if something you can't read or whatever. Okay. So maybe before getting into topology, I'm going to recall maybe what we know about metric spaces. Who has worked with metric spaces before and is like very comfortable with them? Sign of hands. Okay. So I'll still give quick definitions for those of you who are not too comfortable with them yet. So what we do with metric spaces is we basically care about distance. So we have a space which we denote by x, and then we have some function of distance. And maybe one example would be if you take the real line and as distance the absolute value. That would be like some very standard metric space. What we expect from the distance are like 3 points, which is separation of points. You say that 2 points are at positive distance of each other unless they're the same. And otherwise the distance has to be 0. You say it's symmetric, so that's pretty intuitive. The distance between x and y is the same as the distance between y and x. And then you have some triangle inequality that says that the distance between y and z is shorter than the distance between x and z is shorter than the distance between x and y plus the distance between y and z. So maybe that's pretty obvious one. You can also have like very kind of degenerate, weird, trivial examples. If you take any space and you say that the distance between x and y is 1 exactly when x is not equal to y and 0 otherwise, this also gives you a distance, so you can put a distance on basically anything you want. Okay, so that's metric spaces. That's a bit more concrete, I'd say. What we do when we talk about topology is that we kind of forget, like, we want to keep the notion of nearness, but we forget about the quantity distance. We can't quantify the distance. So maybe a definition. What's a topological space? So again, you have a space X and a topology. Topology, which is going to be what we say to be the open sets in our topology. Maybe for those who didn't work too much about them, when I talk about open sets, you can think about open intervals on the real line. That gives you a good intuition on how things maybe should behave. So, as I said, the topology is going to be the collection of open sets. It's going to be a collection of subsets of X, and we require that the empty set, the whole set are open, that any union, so also infinite of open sets, is open, and that any finite intersection of them is as well open again. So we've talked about open, maybe quick. No, we also want to know what closed is. If we know what open is, we have closed interval on the real line. We just said that closed is the complement of any open set. So I don't think I need to write this down. Okay. So maybe a quick remark. If you combine the fact that any union of open sets is open and that a closed set is just a complement of an open set, you can see that any arbitrary intersection of closed set, I'm going to denote them by C, closed sets is again closed. Okay. So what we're going to need maybe is going to be the notion of basis for a topology, which we're going to use later. We say that a collection of subsets forms a basis for some topology. If so, you have a collection of sets in your basis. You say that it's a basis if the union of the B alphas is the whole space, so they cover your whole space. And whenever you have two basis elements, B alpha, B beta, say, and a point in their intersection, you require to have a basis element that's containing the point in their intersection and that is contained in the intersection. If you have a basis, then you can get a topology by taking any unions of basic open set. Okay, maybe some examples. So as I said, we talked about the real line before. This actually gives us a topology as well. But we can consider, for example, the Euclidean topology on R. And this is going to be all the union of open intervals. So open intervals are going to form a basis for this topology. Again, you can have very trivial examples. You can take the set with two elements, and you say that your topology is consisting, well, you need to have the empty sets. You have 0, you have 1, and their union. So actually any possible subset, this is called the discrete topology. And also, if you have a collection of topological spaces, you can consider their product. So it's going to be interesting because if we have topological spaces, we can then easily build new ones out of them by just taking products. And the product topology, which we'll consider, has as basis all products of open sets. So it's going to be a product of the U alphas are required to be in the tau alphas. And then you also have this technicality of expecting the number of alphas such that the U alpha is not the whole space to be finite. Otherwise, it's called a box topology, and you can have some messy stuff when you go to infinite products. Okay. And okay, how's everyone doing so far? Too easy, too hard? Those who never saw topology metric spaces too much before, any questions, complaints? Okay, so let's get into what we want to do. We're going to actually want to talk about compactness and convergences of sequences today. That's where we're going to hunt our lines. So what does it mean for a set to be compact? We say that a set is compact if whenever you cover it with open sets, as many as you want. Formally, this means X is the union of some U alphas. Then you can find kind of a finite subcollection of them. Finite. That still covers the whole space. So that's still X is the union of U alpha, but just alphas in J. So if this is satisfied, we say that our space is compact. Okay. Maybe now our first theorem. It's the Tychonoff theorem. I'm not too sure about how to pronounce his name. Tychonoff. That's actually a pretty cool theorem. The statement is as follows: if you have a collection of topological spaces which are all compact, then their product with the product topology we defined just before is compact as well. This is actually a pretty hard theorem. Turns out it's actually equivalent to the axiom of choice. But let me maybe just give you a sketch on why this should be true for the finite dimensional case. So this is going to be, I don't know if I can write proof. It's going to be a sketch for the finite case. So yeah, simplifying quite a lot. But still gives kind of an insight, I think. So first of all, notice that if you want to prove the finite case, you just need to prove the case n equals 2, or like you have 2 compact sets, because then if you have 3, you can just take the product of the first 2 first, and then add the third one afterwards. And if you have 4, well, you just iterate. So you have 2 spaces. So now I'm going to call them x and y. And you consider their product. And you have some cover with basic open sets. So what are going to be basic open sets? They're going to be an open set of x and an open set of y, and you take the product of the 2, and so it's going to give you kind of boxes like this, maybe the colors. So you have a cover with boxes. Well, it just goes on. Well, it covers the whole space. And what you want to say is that you can find a finite subcover of it. So what you do is you take a point in x, you fix some x, and you consider the line above x. This line is just going to be the same as y. So you consider the line x cross y, which is just homomorphic to y. And so we know that y is compact. So this line is actually going to be covered by only finitely many of these boxes. So you pick some of these boxes that cover your line. Finitely many. And then you look at kind of the range you have left and right in your boxes. And because you have only finitely many, you can kind of take the minimal length of all of them. That's going to be non-zero, because it's everywhere non-zero and you only have finitely many. And this gives you kind of the minimal rectangle that's covered by your finite sets. So this is going to be of the form, well, it's not an interval, it's an open set in X cross Y, which is going to be contained in your union of finitely many U alphas that were alpha X, maybe, that were above your X. So now that we've done this, we can do this for every X. And so around every X, we get an open set. Again, X is like this time we use the compactness on X. So we can find a finite subcover of X. And So you consider only the x's from this finite subcover. Above each of these x's, there's going to be like kind of this rectangle. And the union of all these rectangles is going to cover your whole space. So this is a finite union of rectangles, and in each rectangle is covered by finitely many opens you started with. So that's how you get your finite cover. Why are we interested in this? I'm particularly interested in the following set, which you'll understand why later. 0, 1 to the power 0, 1, the interval, is compact. Okay, maybe what does it mean to be power an interval? That can be kind of confusing maybe the first time you see it. How I like to see it is that, for example, when you think of R3, it's kind of as if you had 3 copies of R. 1, 2, 3, and each line is R. And picking an element in R3 is actually the same as picking a function that goes from 1 to 3 to R. And it's going to send 1 to your first coordinate, 2 to your second coordinate, and 3 to your third. So that's one way of seeing R, which is pretty handy because you can generalize it to 0, 1. You can say that actually elements in here are just like functions from the interval to the 2-element set. Is that too small? Yes, it's too small. Okay, I'll write bigger. Okay, so I claim it's compact. Why can we apply the theorem? So we have a product of spaces. And if they're compact, then the product is compact. Why is the 2-element set compact? Well, you only have finitely many, You only have finitely many opens. So you're always going to have a finite cover. Okay, so it's compact, nice. Now, what do I want to say? I want to talk a bit about compact sets. Suppose that you have a proposition. So you have a compact space, and how nicely does it behave? One nice property is that if you have a collection of closed, non-empty, closed sets, any collection you want, such that its intersection is empty, then there's actually a finite J and J. There's a finite subcollection of them, such that still the intersection is empty. Okay, that's direct. Why is it direct? If you have closed sets whose intersection is empty, you can just consider the open sets, which are their complements. And then these open sets are going to cover the whole space. And because they cover the whole space, they are a cover. You can find a finite subcover of them. And then you go back to closed sets. Maybe a picture for this. Or like, is this clear? Okay, mostly clear. I'll be happy with this. If it's not clear, feel free to ask questions afterwards or take this as granted. Okay. So, corollary, if you have a compact space X and you have nested closed subsets, so C1 is in C1 contains C2 contains C3, such that the CI's are non-empty, then their intersection is going to be non-empty. Why? If the intersection of all these closed sets was empty, we'd be in this case. We could find a finite subcollection of them that would be empty. So say you have, so if the intersection is empty, there exists a finite subcollection of them that still satisfies this condition. And then, because they are nested, the intersection of all of them is just going to be kind of the highest index, the smallest one. And we assume that it's non-empty. So, okay. So now we're pretty good about compactness. Just need to give you a short something on what we want to talk about with convergence. And then we're finally ready to go hunt the lion. Okay. So convergence. What does it mean to converge? In metric spaces, that's the most common definition, and I think a lot of people will be familiar with this one. If you have a sequence of points, you say that it converges to X if, like, you have this thing you should, after first year in mathematics, you can, like, just repeat in your sleep that, like, oh, for every epsilon positive, you can find a big N for all small n bigger than n. The distance between xn and x is going to be smaller than epsilon. So what does it mean in topology to converge? We don't have a distance anymore. So what does it mean to get closer and closer? If we can't measure it, we're going to say that 2 points are particularly close if they're in a lot of common open sets. So what's the definition going to look like? You say that xn converges to x if for every open set U that contains x, there is a n for all n bigger than n, xn is in U. And maybe remark, if you have a metric space, you can construct a topology that's going to be induced by the metric by taking balls. So if you take the open sets to be, or like basic open sets, to be the balls of radius epsilon centered at some point, x, so that's going to be the y such that the distance between x and y is smaller than, or maybe r is a better letter here. You can have this induced topology by the metric, and in metric spaces, these two definitions are gonna correspond, because if you have a point x, then you can take as u's, you can take the balls of radius epsilon centered in x, and then what we're asking here is exactly that you get closer and closer as in metric spaces. All right. We're going to be interested in sequential compactness. It's a different notion of compactness. But what does it mean for a space to be sequentially compact? We say that X is sequentially compact if for every sequence, xn, you can find a converging subsequence. So you can jump some terms if you want, but you need to find converging subsequence. And we're going to be interested in how much this is the same as being compact. Because it turns out that sometimes it is, but it doesn't have to always be. And today we want to show that actually in metric spaces, compact spaces are sequentially compact. Why is this not always the case? Maybe the example we considered before. Why was I interested in this weird example? This space is compact, as we've shown, but it's not sequentially compact. Why is that? So we're going to use decimal expansion of a number. What I do is I say Fn is going to be my sequence of elements in here. And so Fn, remember what was Fn an element in this? It's a function from 0, 1 to the 2 element set. And I say it's going to send x to xn, where like x can be written as 0.x1, x2, x3, and that's its decimal expansion. If you take this sequence, I claim it's not, it doesn't have any converging subsequence. And why is that? You give me a subsequence, fnk, and I show to you that it's not converging. I take the number, the point x, which has the decimal expansion that will be, which has like x and k is 0 for k odd and 1 for k even, and then the rest you put in whatever you want. This is going to be a point in 0, 1 interval. And then I consider the open u product of u x's, x and 0, 1. That's going to be given by ux is the whole set all the time, except when we're at this x naught, maybe I'll call it x naught. If x is x naught, I can take say 0, or I can take vx, which would be the same, but you take ones here. These are two open sets. And basically what our subsequence is going to do, at nk odd, it's going to land into this open set with the 0, and at n even, it's going to end up into the other, so it's going to jump back and forth between the two open sets, so it's not converging. Whew. All right, maybe you deserve a little break. I think imposed quite a lot of basic topology for you, on you for this small of a time. So before we get into lion hunting, which we have all the necessary weapons for now, let me tell you a quick joke. So, I mean, I like topology quite a lot, but I'm not a big fan of stats. I might do myself a lot of enemies now, but here's a joke about statisticians. So it's 3 statisticians that go hunting. So they go again with their guns, and then suddenly they see the lion, you know? So the first statistician takes his gun, aims, shoots, and misses, like 10 feet to the left. So he's like, oh, shoot. And then the second statistician takes his gun, aims, shoots, 10 feet to the right, missed the lion again. And then the third statistician jumps in joy and says, hurrah, we got the lion. If there's any statisticians in the room feeling bad now and wanting to tell me jokes about topologists later, I'm gladly hearing them. Okay, so let's hunt the lion. What are we going to do? We're going to prove the following theorem, which says if X is a compact metric space, then it is sequentially compact. Okay, and we want to prove this. How is this related to lion hunting? Well, we're going to take X is going to be our Sahara, and then we're going to have, what do we want to show, maybe? That's a good start. We have a metric compact space, and we want to show it sequentially compact. So we start off with a sequence. That's a sequence in X. And we want to show that it has a converging subsequence. So maybe, I don't know, we're going to have our sequence that's going to be points. So that's our xn, so 1, 2, 3. And this is going to be like the tracks of our line, and we want to track down the converging subsequence. How are we doing this? We know that X is a metric space. So it has a distance, and in particular, it has the topology induced by the balls I talked before. And I can consider balls centered in X. Maybe I'll write on this side. Centered in X of radius, say, 1/2. Okay? You can have a ball like this around every point in your set. That's going to be quite a lot, potentially, of open sets, but we know that X is compact. So you can find a finite subcover of X with balls of radius 1/2. And now what we want to do is apply the pigeonhole principle. So it's like we have finitely many balls, and we have infinitely many terms of our sequence. So one of the balls, at least, has to contain infinitely many terms of the sequence. So maybe say it's the middle one here, because it's big enough for the rest of the picture. So maybe the sequence goes out of it again, but we just know we have infinitely many points of our sequence in there. So you pick x1, that is such that the ball centered in x1 with radius 1/2 contains infinitely many xn's. And maybe that's a bad notation. I'll call them A. It's centered in A, so A1. And then you can also call maybe B1 the first xn in BA1 1/2. With the first, I mean the lowest index. So, okay, now we kind of know that our line is moving a lot into this circle, but it might still be a pretty big circle, so what we want to do is get closer. So what we do is we cover the ball with balls of radius 1/4. Okay, maybe I'm a bit lying to you now. What am I doing exactly? Is we have our ball, so the ball A1 of radius 1/2. What I'm doing is I'm taking the closure of it. So this is going to be basically the radius you take less or equal to, but there's a bit more hidden behind it. So this is going to be closed and actually compact. So we can cover it with finitely many opens in X, and then you can also take maybe, I mean, if you want, you could take the rest of X to be one open, so the complementary of this closed ball. So you have a cover of X again, and then you take a finite subcover, and this gives you the cover of our ball with smaller balls. So Again, we know that we have infinitely many terms of our sequence in the ball BA1 1/2. And we cover it with finitely many balls, same idea as before. One of the smaller balls has to contain infinitely many of them. So you call it A2 such that same BA2 contains infinitely many, well, maybe I write it down because BA2 of radius 1/4 contains infinitely many xn, and you call B2 the first element in this ball, and well, you want it to come kind of after B1. So, well, the first, potentially after, the first after B1, potentially after B1, to be in the ball. And you go on like this. You consider AN such that BAN of radius 1 to the 2 power of n contains infinitely many terms. You have the Bn, that's the first term of the sequence inside this ball, so you get closer and closer and closer. And this actually gives you, finally, a subsequence, the A case, which is a subsequence of the xn's, that always such that AK is in the ball of radius. Sorry, here we're talking about the BK, of course. The BK are the tracks, the first tracks we find inside our circle. So BK is in the circle, the ball BAK of radius 1 to the 2 power of k. And I claim that these BKs converge. And why is that? So they're in these balls. So in particular, they're in the closure of these balls, which is a bit bigger in some sense. By a proposition we've shown before, because these BK are nested, they're gonna have a non-empty intersection, which is gonna contain all the BKs. Well, there's too many Ks. Bad notation. But, I mean, it makes sense, right? So it's going to contain all the BKs. It's going to be a non-empty closed set. And because of the radius we picked, the radius are going to 0. So basically, we're getting closer and closer and closer and closer. So for every epsilon, we can find points such that starting from that we're in a certain ball of radius smaller than epsilon, and then we're fine. Okay, that was it for my talk. Thanks for listening to me. Maybe would like to precise that no animals have been harmed during the making of this talk. And if there's any questions, I'm glad to take them now. Otherwise, see you at the apéro. Yes.
Can you quickly explain why this approach would not directly work for non-metric spaces? Like how we really use the structure of a metric space?
Well, we're using it pretty crucially by saying, like, using this structure of balls, that we can get smaller and smaller inside of each other, and that we have this definition of convergence with the epsilon. If you have a general topological space with potentially weird opens, you can't impose an open set to be small enough for an epsilon to be contained, or like, because basically the idea what we have here is that we have our x, and we want to say that our sequence of xn's is converging to it. And what we're saying is that basically for every open you give me around x, I can move a little epsilon around x and stay in that open. So this open is going to contain some ball of radius epsilon. So it suffices to show that our sequences contain any ball of radius epsilon, which is something you can't do for general topological spaces. Yeah?
Is this last theorem a generalization of Bolzano-Weierstrass?
Is it? Yes. Any other questions? All right. Well.
Thank you for coming and for presenting this book. I will be going to the math gallery to the Japanese, and yeah, that made me think you